Good morning, everyone. Today we have the video lecture and of a rectifier. Then in next lecture we are going to be cover full wave rectifier. Why the rectifier is needed? Some circuitry, some applications needed DC current or DC voltages. But basically, home supply in India is a AC. How to be convert AC signal to the DC? The rectifier is using for the purpose of this conversion. Let us look into that. We have the black diagram corresponding to this. This black diagram includes step down transformer, a rectifier and load resistor. Step down transformer will step down the input voltage. Basically the input voltage is a high voltage. It is around the 220 voltage. This 220 voltage is not purely converting into the DC, which is going to be make it to step down. Okay, and then it is applied to the rectified circuit. Then it is going to be drawing the voltage from the rectified circuit through the load resistor. Here rectifier is of a rectifier, maybe a full wave rectifier, but after conversion what the voltage you are going to be get across the load resistor, it's not purely DC, it is a pulsating DC. And to make it to convert into purely DC, again another circuit help is needed. We are going to be cover in this session of a rectifier. In the software rectifier we have to be monitor the some of the parameters which are rectifier parameters. Average component, that is called the IDC, it means that DC current. We are going to be having output of the rectifier is the IDC, and output of the rectifier is maybe a VDC. It means you can be considered current and voltage in DC only. Here RMS load current and ripple factor, voltage regulation, voltage rectification efficiency, and peak inverse voltage and form factor. These are the parameters we are going to be discuss in the software rectifier. At the same time, in upcoming classes these same parameters also going to be discussed for the full wave rectifier. How to be make it to compare these parameters between off wave rectifier as well as the full wave rectifier. Let us look into this off wave rectifier. Off wave mean half of the input signal is going to be rectified. Let me consider the diagram. Here we have the n:1 transformer is there. It means number of turns present in the primary, number of turns present in the secondary is going to be defined by this ratio n:1. Basically n:1 indicates that one it is a step down transformer. The amount of voltage is applying for the primary winding of the transformer, same amount of voltage is not going to be induced in the secondary winding of the transformer, which is going to be step down, might have the producing or inducing in the secondary, depends upon the number of turns which are present in the secondary only. But you have to be remember the input of the rectifier is always AC signal. It is having generally home supply is the 220 volts, 220 RMS, as you can be say that when it is a 58 this is there. You can convert this one into RMS value into peak value. It is you know that one RMS is equal to Vm by root 2. Vm is equal to RMS into root 2. The notation was given 220 RMS. So can be written like you know that one peak voltage like RMS into root 2. So 220 into root 2. Denominator like you know that one. It is the Vm. It is the peak value. When you say that one in mathematically, how to write the equation for the voltage or current, that is you can say Vm sin omega t, it is a voltage equation. Im sin omega t, it is the current equation, where Vm Im is nothing but peak voltages or peak currents. and omega t is nothing but angle in radians. Angle in radians is going to be changes with respect to time. That's what we are writing, it is omega t. T will impact over the radian or angle of the signal. So let me consider the secondary of this circuitry. It consisting of the diode as well as the load resistor. This is having the voltage is going to be induced across this diode, this secondary transformer coil, that is going to be step downing by using the step down transformer. The amount of current which is passing through this diode is nothing but Im. Let me consider we have the input signal is like this, that you can be named as a supply voltage or you can be say supply current. Vm is nothing but peak amplitude of the input signal. You can also denote like here also Vm, but this Vm is nothing but negative because the negative of cycle. But this one is the positive of cycle, it is having plus Vm. Here we have the Vm, it is negative Vm. Yes, from 0 to pi radians you can have the positive of cycle, having the positive peak is Vm. From pi to 2 pi we have the negative of cycle, having the peak value is minus Vm. You should be understand over the x-axis omega t. Omega is nothing but angle in radians is going to be changing with respect to t. Yeah, having the input signal is expanding from the 0 to 2 pi radians. Let me consider for the half of the cycle from the 0 to pi is going to be converted into DC. Let me consider in the half of the cycle in the positive duration from the 0 to pi, diode will become forward bias. When the diode will become forward bias, this loop is going to be closed. Then some amount of current is passing through this circuitry. Then you can be understand some Im is going to be existing through the circuitry. When Im is passing through the RL, you going to be uh, going to be having voltage across the RL. That voltage you can be say it is nothing but load voltage, or you can be write like that one load voltage or DC voltage. When that DC voltage is depends upon the conversion or number of turns in the coil and efficiency of this your rectifier. All these things are going to be impact over this how much voltage there across your load resistor, depends upon the how much amount of current is passing through this loop. Here let me consider the equation corresponding to the current which is passing through the load resistor, that denoted like that one IL. This IL is going to be existing when the diode in forward bias. Diode will become forward bias when you have this one positive half of the cycle is applying for the input of this circuitry. Then you can understand IL is equal to Im sin omega t in the duration of 0 to pi. But what about the pi to 2 pi? There is no current is going to be existing in the loop because diode is no open condition. It is like an open circuitry. So there is no current is passing through this. You can have the voltage across the RL due to the current passing through the load resistor is Im only. This Im is going to be existing in the 0 to pi. That's what you can be say it is a half-wave rectifier. Let us go with the some parameters related to the half-wave rectifier. IDC, it's nothing but area under the curve of the angle variation is from the 0 to 2 pi, because you are having how much amount of conversion is taking place from the alternating current to the DC current. That DC current you can also known as the average current. You have to be include the total area, the angle variation from 0 to 2 pi, like that one 0 to pi as well as the pi to 2 pi. You can write the equation IDC is equal 1 by 2 pi integral with interval 0 to 2 pi IL into d alpha. This alpha you should be remember. Alpha is equal omega t. To make it to understand easily, just we have denoted like alpha is equal omega t. So then you have to be substitute. Okay. Here how to be extend the equation like 0 to pi, as well as here the equation is going to be extended from the pi to 2 pi, something like that. Same equation is going to be written like that one 0 to pi as well as pi to 2 pi. In the 0 to 2 pi, pi to 2 pi, there is no current is passing through the load resistor because diode is in open circuit. So you can have the current passing through the load resistor when have the diode is in forward bias. That you can be denoted like that one IDC is equal Im by pi. Then VDC, it is equal to IDC into RL. Like that one according to Ohm's law, you can write V is equal to IR, or you can write that I is equal to V by R, or R is equal to V by R, I. These are all formulas corresponding to the Ohm's law. Just I have written VDC is equal to IDC into RL. What is the IDC? According to the notation given corresponding to the off wave rectifier, IDC is equal to Im by pi. Then VDC you can write is a voltage drop across the load resistor. When you consider, okay, when you consider, just simply have written EDC in terms of the IDC, but actually what the VDC EDC is nothing but is a voltage drop across the load resistor. Do you have only one resistor is present in the total loop? No. Practically we have the additionally two resistors are going to be considered. One is the resistance corresponding to the secondary coil of the transformer. Another resistor is forward resistance of the diode. These two resistance are also going to be impacting over this one. How much is the voltage is going to be drop across the load resistor. So this RS, RF, RL, which are all in series with each other. To know the how much voltage is drop across the RL, you have to apply the voltage dividing rule. That voltage dividing rule is help you to calculate the voltage across the particular resistor when it is part of the series circuitry. VDC is equal to VM RL divided by pi of RA plus RS plus RL. So you have to be remember this one. Here we have the Vm by pi is there now. You have to understand that one. What is the VDC by using this circuitry. You can also make it to move to the denominator. Then it is divide the all the resistor. Then you can have this 1 plus Rs plus Rf divided by RL. RL gets cancelled so that you will get the 1 here. Then this is the equation is particularly can be determined used to calculate the DC voltage when you consider the RS and RF and RL. If suppose if you consider RL is infinite, means there is no load for the rectifier circuitry. When there is no load, when there is no load, the load resistor is open circuitry. Then what is the resultant voltage of the DC? It is equal to the Vm by pi only. Then what is the IRMS? IRMS is nothing but root mean square value. Here IRMS value how you are going to be determined. Here two things are there. IRMS basically you can be write like Im by root 2. VRMS you can be also write like that one Vm by root 2. But we have to be determine IRMS, okay, for the off-wave rectifier. Basically you can write the equation for the IRMS calculation square root of 1 by 2 pi integral 0 to 2 pi interval I square d alpha is equal to omega t. Just you have written that one I is nothing but the current which is passing through the circuitry. Can be written like I is equal to Im sine omega t. Omega t was replaced with alpha. But in equation it was written like that one I square. So you can write like that one I am square sine square alpha. Then I am is the independent of the alpha. So just you make it out from this integration. Okay, I am square by 2 pi. Integral 0 to 2 pi sine square alpha d alpha. The resultant value after integration and squaring you will get is Im by 2. This is the IRMS for the off-wave rectifier. This is the IRMS of the load circuit you can be understand. Okay, VRMS for the load circuitry is Vm by root 2. VRMS for the secondary of the transformer is Vm by root 2, because here VRMS is corresponding to the full wave, but here VRMS is corresponding to the half wave. That is the difference. Ripple factor, RMS value of the alternating component divided by average value. What is the ripple factor? What is the amount of alternate current is available after the rectification of your voltage or input? Though you converting the alternating current to the DC current is going to be consisting of the amount of alternating component. That percentage of alternating component of the DC existing current or DC existing voltage, you can be called it as a ripples. Those ripples need to be suppressed. Actually those ripples need to be less, then only you can have the output is purely DC. When there is a more number of ripples means there is not having the perfect rectification process. That you have to be understand. The purely rectified output is like looks like a DC, but when you have this one alternating component is going to be mixed with the converted DC, is nothing but it is called the ripples. Then you have to understand I dash is nothing but AC current which is available in the DC component of the rectifier output. What is this one? IDC. It is a purely DC current which is existing in the output. Means you should understand, in the converted output or rectified output, it consisting of the AC component or a DC component, or else you can be say AC current or a DC current. This I dash is nothing but AC current is presenting in the DC current. IRMS, RMS value of the AC current which is presenting in the DC current of the rectifier output. Ripple factor, you can be right like that how much amount of the AC current is available in the rectifier DC current, that you can be have the ratio of I dash RMS divided by IDC. You can write this one, I dash RMS is equal under root of 1 by 2 pi 0 to 2 pi I dash square d alpha. You can, what is this I dash is nothing but is a presenting alternate current of the rectified output. So you can be say the total amount of current which is presenting at the rectifier output is nothing but IDC plus I dash. This I dash you are going to be determined is equal to the I minus I dash. I dash RMS square is equal 1 by 2 pi integral 0 to 2 pi I minus IDC whole square d alpha. This is going to be using the trigonometric equation a minus b whole square, a square plus b square minus 2ab. That formula is using and extending like this. So resultantly you will have this one I square RMS. This is going to be noted as a IDC and this is going to be noted as a 1. Then you have to understand ripple factor is equal I dash RMS divided by IDC. Then you can write this one under square root of IRMS square minus IDC square divided by IDC. This is the thing you have to be understand. Means this is noted like a IRMS square and IDC is equal to I dash RMS whole square. Then square will become here. You can have this one IRMS square minus IDC square square root divided by IDC. This one IDC. This will come here. Then you can cancel the IDC at numerator and denominator. Remaining terms are IRMS divided by IDC whole square minus 1 under square root. You can also substitute IRMS is equal to Im by 2 and IDC is equal to Im by pi according to the previous derivations. Then you can have this one Im gets cancelled. You can have pi by 2 whole square minus 1 under root. You can also denote it like it is going to be equal to the 1.21. Voltage regulation. It is the ratio between the difference voltages between the no load DC voltage and full load DC voltage to the full load DC voltage. It's a voltage regulation up formula. Full load means when there is existence of the load resistor, that is called the DC voltage of the voltage regulator, that is called the full load. When there is no load resistor means RL is tends to infinite, that you can be called it as a no load. You can write like this: IDC is equal Im by phi according to the previous slide discussion. IDC you can also write in terms of the resistors Vm by pi or a plus Rs plus RL. You can write like this. You can move this denominator to the multiplication to IDC. Can be write like IDC into Rf plus Res plus IDC into RL is equal Vm by pi. Vm by pi is nothing but VDC no load, and IDC into RL is nothing but VDC full load. According to discussion, this VDC no load minus VDC full load can be determined like that one IDC into RF plus RS means VDC no load minus IDC RL. When you move here, then remaining term is IDC of RF plus RS, that I have written here. At the denominator, what is this one? VDC full load. VDC full load is nothing but Vm by pi minus IDC RF plus RS. Just I have written here. This is called percentage of voltage regulation for the off-wave rectifier. Rectification efficiency means how much amount of AC power you are giving, how much amount of DC power you are delivering to the load is going to be determined by using the rectification efficiency. We have the formula like that one PDC divided by PAC. It is equal to IDC square into RL divided by IRMS square into RF plus RS plus RL. You know that one P is equal to I square R formula. Same formula I applied. Here we have the DC component, so that I have written it is IDC square. We have the AC component, so that we have written it is IRMS square. Then IDC square by IRMS square into 1 divided by 1 plus RF plus RS divided by RL. Just you are moving this RL to the denominator. Here RL going to be gets cancelled. Remaining is RF plus RL divided by RL plus 1. If you consider RL is much greater than this RF plus RS, then what happens? This term is going to become 0. What is the remaining? 1 by divided by 1 plus 0 is nothing but it is 1. So remaining term is rectification efficiency is equal to IDC square by IRMS square. Again you substitute IDC and IRMS. The resultant value is equal 2 square by pi square, that is 4 by pi square. It is equal to the 40.6 percentage maximum. That is called rectification efficiency. It means if suppose 100% input you are giving, only 40.6% of the input is going to be converting into the DC power. That is the meaning of that. Peak inverse voltage, maximum input maximum negative voltage can be applied to the diode to capable to having this withstand of the diode. That is called the peak inverse voltage, that is equal to the Vm only. Form factor, it is a ratio of RMS value and average value. You know that one IRMS and IDC. IRMS is called Im by 2, IDC is nothing but Im by pi. So Im gets cancelled, resultant value is equal to pi divided by 2. It is equal to 1.57. Peak factor is equal to the peak value divided by RMS value. Peak value, it may be a current, it may be a voltage. Peak value of the current is Im. RMS value of the current is Im by 2 according to the off-wave rectifier. For full cycle you can write this Im by root 2 basically, but it is written according to the off-way rectifier Im by 2. It is nothing but Im divided by Im by 2. Im gets cancelled, resultant output is 2. That is a peak factor. Thank you everyone. This is today class.